So how's everybody? Good. Any questions before we get started? Oh, everything's screwed up. There. Okay, so we have a lot to get through. A couple of people are presenting. We're going to get through galaxy classification, which is actually pretty straightforward, but there's a lesson in there about how galaxies interact, so we'll talk about groups and local groups in galactic evolution. And then really, really important thing that sets the stage for cosmology, which we'll do after a couple of presentations, is lookback time, and use the speed of light, which is basically instantaneous during your everyday life. Light gets from point A to point B without you really having to worry about the travel time. Not true in the cosmos. So we'll talk a little bit about that, even though we have before, but in the consequences for things on galactic scales. Okay, so galaxies. It's kind of weird. Galaxies in general, chapter 15, and then 16.2 also includes dark matter, which is, honestly, it's a bit funny that they put it in its own section, because it should be mentioned in the same breath as galaxies. I think now we're better. Okay. Here we go. Good. And then Friday quiz on Milky Way galaxy dark matter. I try not to do this, but I'm going to throw in a little bit of this week's material because we're getting pretty close to the end of the quarter. So it'll just be galaxy classification, so Hubble's tuning fork, so-called tuning fork, and then ellipticals, spirals, barred spirals, irregulars, which we'll get to today. Okay, so today will be ellipticals, spirals, barred spirals, and irregulars, which is to say types of galaxies, an attempt to organize them on an HR-style diagram, which turned out to fail, and then the first, the next rung on the distance ladder in this idea of lookback time, which tells us something about how galaxies evolve. So again, the big story is that we're trying to do all of the things that we did for stars for galaxies. We talked about their physical properties like mass, composition, age, type, and then we talked about their evolution in time, which is what do they do? Well, stars just spin and maybe spit off some flares. Galaxies are pretty interesting. At least the spirals have spiral arms, and earlier in their lifetime they actually probably look drastically different. There are regions of star forming in the disk, and regions that star forming has been completely suppressed in the halo, but still have stars, namely the globular clusters. So we still have some of this stuff left to talk about, is really the full details of galactic evolution. Are they all the same age, or some old, or some young? And then the fact that obviously they don't all look like a spiral galaxy like our Milky Way galaxy. And it seems like we haven't taken a chunk out of this list, but most of this stuff we can get to today. And it just took so long to talk about galactic mass because it turned out to be a complete landmine in the universe and led us down the path of dark matter. It's still not understood. The problem is well defined, but what it actually is. Okay. So this is Hubble Deep Field. Let me turn the lights out for a second. And again, the idea was the Hubble lights out for a second. The Hubble Space Telescope, when they were calibrating it, nobody really knew what they were going to see because you can't do this with a ground-based telescope. There's atmosphere in the way. And to sit there and basically take light from the same patch of sky for 11 days would be pretty hard because the Earth rotates. But this is what Hubble saw when it pointed at a dark patch of sky, and that's a star with the spiky fringes coming off of it, the refraction fringes. That's a star, and that's a star. And everything else is a galaxy. And very clearly, as well as color, there's also some differences in galactic morphology. So when we did this with stars, we were like, oh, well, some are blue, some are white, some are orange, some are red. And then it turns out that was related to temperature and temperature only. But there's not going to be such a simple answer for what's going on with these red and these blue galaxies because they're actually comprised of billions of stars instead of just one. So that's where we are now. Is how do we talk about different types of galaxies in a naming scheme? Okay, so same thing, a little bit more detail, and just to indicate that it's a really tiny field of view that you're looking at. So this whole thing again is, these little coffee stirring straws. If you look through one of them at arm's length, or about the diameter of a toothpick or something at arm's length, this is a really small patch of sky. So there's so much of this stuff out there. Okay. So here's some close-ups, which make things a little bit more obvious that they're really distinct morphological types. So this is a spiral galaxy. It's got arms. We just happen to be viewing it face on. Well, this is a spiral galaxy too, and even among spiral galaxies, apparently there are some distinct differences. Namely, this one has, just two arms and this central weird bulge, which is almost elongated into a bar. There are these things that look like maybe something's happening, they got disturbed, or maybe they're really young, or they're tiny. And then there's this. And this is not a trick of perspective, is that these galaxies and these galaxies are actually all the same distance. So this giant featureless monster galaxy does not have arms. It's basically a giant bulge. And then there are funny things like this, which seem like a bulge, but with almost like spiral galaxy-type dust lanes on it. So these are the big sets out there. If you had to group these into categories, what do you suppose you would group them into? Actually, this is the extra credit on exercise 9. Make your own galactic classification scheme. There's no really strong physical motivation for this, like there was with M's versus O's, which is just temperature, temperature, temperature. Got a disk or not? Yeah, you divide them along those lines. Sure. Other potential dividing lines. So you could go in a totally different way too, I think. Yeah, color. So you can totally divide them along color lines. And in fact, there's a bit of overlap in between colors. So they're kind of orangey, more reddish galaxies. And then these, especially in the spiral arms, it looks like there's a lot of bluish light, which we now know that if you see bluish light coming from some group of stars, small or big, that means that there have to be what going on, what process. Got to be star formation, right? Because only O stars, which only live for a short amount of time, O and Bs, give off blue light. This is what was chosen. It, just realized that it's kind of arbitrary in some sense, but it's good enough. So S is for spiral. So this is the equivalent of OBAFGKM. A spiral galaxy has a disk. Things are spread out into a disk, and it's got spiral arms, and then in the center there's a bulge of some type. Bulge could be totally prominent and overwhelming, or the bulge could be, just a little clump of stars. But it's a disk, and it's got a central kind of node of stars in a bulge. Okay, I'm going to split those, and SB is for barred spiral, where the bulge is actually elongated in a totally dominant feature. So it's almost like, think about how weird this is in some sense. You almost imagine this as like the stars were all welded together. It's like, like one of those Ice Capades shows, and then there's stars streaming off the edges. It's kind of weird to imagine this arising naturally. But in an SB, or barred spiral galaxy, the bulge is a totally overwhelming feature, and it's elongated into a bar. And, at the end of it, just realize there's S's and SB's, and for you guys, it'll suffice to know it when you see it. Because, again, there's no physical parameter like temperature. And then E is for elliptical. Now, ellipticals don't have to be perfectly spherical. An ellipse, again, is elongated, so it's a good name. They can be basically a perfect sphere of stars, so they've got no disk, no arms, no distinguished features like that. But they can be either perfectly spherically symmetric, or they could be elongated to almost like a total cigar shape. And they can be giant or tiny. And this in particular is a wonderful picture of this monster, which is, you could fit our Milky Way galaxy there. So it's nothing but a bulge. This is a monster. It's like 500 billion stars. And then these elliptical galaxies, which have, just 100 billion, 50 billion, might be orbiting it, or might be about to be eaten by it in some sense. So ellipticals really just mean no disk, no arms. What do you guys notice about ellipticals if we wanted to use a different scheme and use color? What don't you see in elliptical galaxies? Yeah, no blue. So what do you know is not happening in ellipticals? Yeah, no star formation, so something funny is going on. So this in particular one is, we'll explain it later, this monster. But E is for elliptical, okay? So you got S is for spiral, SB is for barred spiral, E is for elliptical, and they can get really stretched out. And you might even ask yourself, how do I know I'm not looking at some, imagine if a submarine was moving right towards you, it would kind of look like a perfect ellipse, right? So how do you know this isn't some monster, hot dog shaped galaxy coming towards you? You kind of don't, but it's okay because it would still be elliptical. And then finally, there are peculiars too, but we won't talk about them. Is for irregular, and these are important for our story. Is an irregular galaxy, they actually tend to be smaller, but they just don't have the symmetry of a spiral and a disk, and they don't have the symmetry of an elliptical. Basically, if it's a galaxy, it's outside of our own galaxy, it's billions of stars, and it looks like you found it in a handkerchief, it's an irregular. Okay. If it looks like some weird combination of the two, that puts it in the peculiar category. Like if it's got dust lanes like a spiral galaxy would, but then there's some giant bulge in the middle or a rash of stars coming out of it, then it might be peculiar. But we won't get too far into those. But I will show you some peculiar galaxies. Okay, any questions about that? And C is still for cookie, but that's not really important. Yes, absolutely. It changes a little bit with time, and you'll see why, but it's almost 50-50. So about 70% of the galaxies that we see are spiral galaxies. And that's actually changing a little bit in time. The really early universe, you see more irregulars. In the more recent universe, which is to say closer, for the Lookback Time reason we'll talk about, is you tend to see a little bit more elliptical galaxies. But roughly speaking, it's like 70-30. And it's usually elliptical spiral. The irregulars and peculiars are the oddballs. Okay. So Edwin Hubble, who's already famous at this point, even though he hasn't really done his super important work of Hubble's law, is the guy who figured out that Andromeda was actually a different galaxy by painstakingly watching somebody take photographic plates of variable stars at the top of Mount Wilson Observatory. He wanted to make the equivalent of an HR diagram, but for galaxies, and he came up with this thing, the so-called Hubble tuning fork. He's Edwin Hubble, so we keep it. It doesn't really mean anything, but I'll tell you what he was thinking, is that the handle of the tuning fork is the ellipticals. And you start at E0, which is like perfectly round, like a basketball or something like that. And as you get out to E5 and E7 and higher numbers, so they're subdivided into numbers, then it becomes more elliptical. So like an E5 would be a rugby ball, and then an E7 would be something more like a what's slightly more squash than a rugby ball? I guess that's true. Yeah. So maybe a football that the New England Patriots use, so it's a little bit deflated. I don't know. And then at the handle, it breaks into the barred spirals and spirals. And then for some odd reason, instead of numbering them, Hubble put letters on them. So SA, SB, and SC. And that basically tells you two things. How defined the arms are and how minuscule the bulges. So these things have very well-defined arms and kind of tiny bulges, like a lot of people. And then out here, the bulge becomes more dominant, and then the spiral arms diffuse. This is the Hubble tuning fork. It doesn't mean as much as the HR diagram means. It's just like a thing. And if you remember the parts and the fact that irregulars and peculiars aren't on it, that's fine. Okay, so what was Hubble thinking? We just keep it because he's famous. So what was going on in 1910, 1920, if you know a little bit about the history of especially this country, is people are having these great debates about whether or not you should do things like teach evolution in schools. Like this was settled in England in 1890 or something like that. So 20 years later, we're trying to figure this stuff out. And so there are these famous public debates and radio debates in between American creationists, young Earth creationists, and evolutionists. So it was like a really hot topic, and it was on the back of everybody's minds. And this is kind of what Hubble was thinking, is that in biological evolution over the succession of millions of years and generations and generations and generations, you start with an amoeba, and then you get a fish, and then you get a human, and there's this evolution towards complexity. Every once in a while you reset with a cataclysmic extinction, but Hubble didn't know that. And he thought that maybe astronomical bodies were like that too. So you have an E0, and it's kind of like a space amoeba, right? It's completely undifferentiated, very simple thing. And Hubble's idea was maybe that if you took an E0 elliptical galaxy and you wait for 4 billion years and just kind of let it hang out and spin, and he actually didn't know that 4 billion years was the right number, but a very long cosmic time, eventually it would evolve into a beautiful spiral galaxy or something like that. So it was really kind of an evolutionary idea that he had, and he thought that time, in a sense, went that way. And we now know that that's almost exactly wrong, but we keep the Hubble tuning fork. And it turns out that you're basically kind of minted as a, right at the beginning, you're minted as a spiral galaxy. Something might happen to you later, but you don't have to evolve out of an elliptical stage. You could just make an elliptical galaxy. So it doesn't necessarily have anything to do with time. If anything, time actually goes the other way, what Hubble thought. Questions about that? So it's not as important as the HR diagram, but it's something that for historical reasons and because we love Hubble, people keep around. Okay. So how do these things interact? We've talked a little bit about the fact that we're on a collision course with Andromeda. So obviously something happens. You have 200 billion stars, and a lot of empty space and a lot of time. Gravity can do its thing and eventually pull them together, and you might have some interactions. Turns out that galaxies, much as stars occur in binaries half the time, a little bit more than half the time, galaxies actually occur in groups, almost always, in fact. So a galaxy actually will have a group. We have our local group, which is like us, and Andromeda are the two big galaxies, Triangulum's a little bit smaller, and then the Magellanic Clouds and some dwarf galaxies that we're going to be munching on pretty soon. This is a picture. Of course, you can tell it's a Hubble image because it's got the puzzle piece missing. Early Hubble image. These are stars. You can tell by the refraction spikes. And there's a spiral galaxy, a spiral galaxy, a spiral galaxy, and an elliptical galaxy, all living in harmony. That's probably a dwarf elliptical in the same group. So this is a group of galaxies. What makes them a group of galaxies as opposed to just things that happen to be close to each other? Any guesses about what the cutoff for being in a group is versus not? Yeah, exactly. In fact, the gravity of your neighbors is the most important thing. And this is almost like half an answer now because you're like, well, gravity just gets smaller and smaller as I get farther and farther. But the real distinct answer is that you're in the local group with somebody if you care about their gravity and you don't care about Hubble expansion, which is, of course, what we'll talk about later today. So these guys are all bound by each other's gravity. They're in a local group together. This is the Hickson compact group, which you've been looking at all quarter on the course website front page. Okay. So the question, I guess, now is, do you think this is stable? So you put this delicately crafted spiral of 200 billion stars out in space, and then you put another spiral of 200 billion stars out in space, and you let time go. Do you think there's some chance of mischief or misfortune occurring? Well, in fact, dark matter might be a problem too, because what does dark matter do to gravity? So dark matter has gravitational influence. So in fact, dark matter, the fact that there's more matter than you see, it's actually making them do what? Yeah, pull towards each other. And then what might happen is they get really close. You have to worry about interactions and tidal forces and things like that, which might not be too good for these, again, beautiful, delicate spiral arms. But we'll get there in a second. So this is our local group. This is obviously an artistic depiction. This is just kind of like everything put side by side with relative sizes. It's, every 10 years or so, it seems like this changes by, 50 billion stars. So obviously don't take the Milky Way, neither picture nor size, too seriously. But that is Andromeda, and that's Triangulum, and this is our local group. aside from all the big ones are spiral galaxies, which is a little bit rare, and that will change, I think, because we will interact. So here are a couple of local groups. This is Hickson compact group. It's a nice one because it's like very diverse. I like it. There are ellipticals and spirals living in harmony. There's ours. We've got a couple of spiral galaxies. This is a random one from the cosmos. It's actually not terribly random, but it's on the other end of things. So this is a whole bunch of galaxies. We'll zoom in on it later, but do you see any spirals in there? What does it mostly look like? Elliptical. So there's a story in that, is that the bigger these things are, they tend to be more elliptical. So these are local groups. That's the next level of organization of the cosmic address. That was the 3 minutes that we'll spend on it. So, yeah. You mean whether or not you can tell it's a spiral at all or something like that? Yeah, so I guess the question in a sense is, if you know, this is a reasonable rephrasing is like, do you think that a very elongated elliptical could be masquerading as a spiral galaxy and we'd never know? It's unlikely because there are going to be some other indicators that something's a spiral. So why would you think that this is a spiral, for instance? Yes, it's got a bulge. Ellipticals do kind of have cores. But it's not, it's a different type of core and a different type of bulge. But there's a second thing going on, is there's this, which spiral galaxies have a lot more of. So you see this beautiful dust lane in the edge on. Whereas if this was like a really elongated elliptical that just happened to be, kind of showing you its profile view, you probably wouldn't see the dust lane. So why do ellipticals not have dust is exactly what we're about to get to, is something happens when you make an elliptical. But yeah, it's not 100% clear, but there are enough indicators as to what an edge-on spiral would be versus just an elliptical that happened to be elongated. Yeah. Jets and active galactic nuclei. Yeah, these guys don't have them, but other ones do. And the reason that you don't see any jets in these really like high fidelity, high resolution pictures is because they're really close. And if something's really close and the speed of light is, not as big of a number as you kind of tend to think of it on Earth, what does it mean if something's far away? So how long is the light taken to get to you? Longer and longer amount of time. So in fact, you're looking back and back in time. And so you see jets around things that are actually really far away and really far back in time, therefore. So there can be jets around galaxies, but not something that's this close and this beautifully resolved. So usually what you do is you see jets around distant galaxies, and there's things called quasars, actually, to get to in a couple of minutes. They can, yeah. Yeah, you have to have a couple of conditions for a jet. So you have to have probably a supermassive black hole in your core, which most galaxies seem to have. But then you also have to have something perturbing you. You have to be interacting with a lot of dust or gas, or maybe eating a dwarf elliptical or something like that. So you have to have stuff like funneling into the black hole and being spun around and ripped out. And then, now at like 13.7 billion years after the Big Bang, it's not, it's less common than it was in the early history of the universe. You had more stuff colliding. So the jets that we see come from things that are much farther away, which actually means much farther back in time. Because in the earlier history of the universe, things are a little bit more chaotic. So to see a jet on something that's really close, something that's, like 500 million light years away or a billion light years away, means that, it was very unlucky or very lucky and something fell right into the black hole, for instance. So. Okay, so let's zoom in on this giant group or cluster. And we saw something like this before. there are these streaky things, which are gravitational lensing, and all the mass is pulling the stuff around. These are some foreground stars. You can tell by their refraction spikes. And again, what do you notice about clusters? And this isn't a really lucky or unlucky one. This is really indicative of a big cluster of galaxies. What types of galaxies do you see predominantly in these big clusters? Ellipticals, right? They're really red. I don't see any dust. I don't see any features or arms. Any explanations as to why you only see ellipticals in bigger clusters? Yeah, what would they possibly do? It's actually more violent than you suppose. So let's say that you're a spiral galaxy and you're born with your, pretty spiral arm butterfly wings, and then there are all these other galaxies around you. Do you think you might interact with one of them? Think they might rip off your pretty spiral arms? Yeah. And then leave you as nothing but like a bulge. Yeah. So in fact, this is what's going on. And Hubble was exactly wrong, which might be why we keep his Hubble tuning fork. So that's actually one of our clues about galactic evolution. And there are two ways of doing it. One way is just looking at clusters of galaxies and observing how they interact, because when you look at a cluster of galaxies, that is a snapshot of how they're interacting with each other. Or secondly, you can look at really distant galaxies, which is also looking far into the past, and that's so-called lookback time. Okay, so these red elliptical galaxies, they're much more common in bigger clusters. The lack of blue stars, those are foreground stars in our own galaxy, means that they've lost their dust, they've lost their ability to make new star formation, they've got their, predominantly GK and M stars, and they're just going to be burning away with what they got. So the explanation for that is that, and we see this actually, so you see these pictures, another beautiful Hubble image, is that these are two spiral galaxies that are actually interacting. So you can tell what used to be spiral arms, and you see this rash of new blue star formation as the shells of dust get bumped into each other, and it triggers a lot of new star formation. Is that when these things interact, you might actually start with two spirals and then end with maybe one elliptical or something like that. And computer simulations really support this idea, as you can start with two spiral galaxies and they interact and they kind of rip each other apart, and you're left with a single core. While this happens, a whole bunch of, a huge rash of star formation will be triggered. Let's see if we can do this without the ad. I think so. Okay, so there's a representation of the Milky Way galaxy, and this is time from now. This is 1 billion years in the future, according to the simulation at least. That's just the camera zooming out. And there's Andromeda coming for us, and little Triangulum is going to join in too. So now you start seeing the tidal forces will start deforming the shell of stars in the arms, and then as they sweep through. So what you should also see is this huge rash of supernova going off as all the dust gets perturbed by the stars flowing through it. You actually see a lot of new star formation, so that's why it seems to be less blue. And then we'll settle out into a single, eventually elliptical galaxy. So this is the fate of our galaxy in about 6 or 7 billion years. Yeah, so we have a couple of pictures of this happening, and the stars in the halo, like the globular clusters, they just get perturbed, and they're gravitationally bound to each other. But something funny happens, and you get a really interesting and incomplete insight about dark matter from how the dark matter in the halos interact. And it doesn't act like gas, and it doesn't act like stars. So dark matter in galactic collisions acts like dark matter, like it doesn't stick to anything. So it actually gives you some insight about what it is or what it isn't. It's hard to say more than that, actually, I don't know. But this is our future. This is going to be a really violent event, aside from the supernova. Remember the grapefruit model? Yes, right? So you have, the interstellar distances are just so great that it'll be more like milk flowing into another glass of milk. So it won't be like stars bouncing into other stars. Could be, yeah. Yeah, this is a tough one. If you can, to say that they'll find each other just because they have a lot of gravity isn't quite right, because they have this angular momentum issue. Is that if they were to just like find each other dead on, that would be pretty amazing because they're so compact. What'll actually probably happen in a galactic merger is the two supermassive black holes will kind of come in and they'll start spiraling, and it'll take a very, very, very long time for them to radiate away and get so close that they actually merge. So you'd have to be tremendously lucky to get a spiral like right off the bat. Black hole in spiral. Our ability to detect black hole in spirals is less than a year old, so it's kind of hard to answer that question. But just the odds and the sizes of the things make it pretty difficult to, say that, oh yeah, every time we have. And galactic mergers are actually pretty rare. So in any given slice of the sky. So yeah, it would be interesting because maybe it makes you think that in ellipticals there are 2 or 3 galactic cores, or in that monster elliptical it's got 7 or 8 supermassive black holes wandering around. It's actually kind of terrifying, actually. But here's just a gallery of Hubble images of galactic interactions. It's common enough, so this happens a fair amount, and they're very pretty. And this is some artist depiction of what'll happen to us. So this is actually, I think it's from Colorado or something. This is actually what Andromeda looks like now. Your eyes wouldn't be good enough to see it quite that bright, but it's barely visible at the edge of human perception. Yeah. Yep. Speed of light. Yeah, totally. So it's not light, but if you're a perturbation or a particle that has no mass, you can travel at the speed of light and no faster. So to particle physicists, they would say the graviton, the fundamental thing that transmits gravity interaction, travels at the speed of light. For a classical physicist, they would just say the ripples in space-time, because they don't carry mass themselves, travel at the speed of light. And that was kind of put in by hand in general relativity. It's right now. Yeah, so those signals, the black hole in spiral has been traveling for 1.4 billion years before it got to Earth. It's a very tiny signal. And that wasn't a supermassive black hole in spiral. That was 2 30 mass black holes. So it probably happened from a single giant supernova going off that made 2 black holes that really quickly in spiraled. It's probably the best guess. So in about 1.5 billion years, if you eat vegan and exercise, you're still live, this is what you will see. There'll be a giant spiral galaxy in the sky coming towards us. And then gianter and gianter still after the next billion years. And then during the merger, you'll actually see 2 things. One is the deformation of all of our arms as all these stars flow through our stars. And secondly, there will be just this tremendous acceleration in the rate of star forming. So you'll see young supernova, and you'll see the dust in the gas lanes being consumed. It'd be pretty beautiful. You get more supernovas. In a just normal galaxy, you get about a supernova per century. Now this will work up to one every 5 years. I don't know, something like that. And then as it passes through, more star formation, crazy times. Maybe Earth gets sterilized by. There's something a little bit misleading about this. This is about 4 billion years in the future, at which point our own sun will be a red giant. So you actually wouldn't see this. You just see the licking flames of Hades from our red giant sun. And then in this fictitious Earth that doesn't have a red giant sun on the other side, then you see the deformed spiral arm, and then this now broken Andromeda galaxy is passed right through us. I don't know. Yeah, the clock's ticking. The average lifetime of a mammalian species on planet Earth is 1,000,000 years, and we're not close to that yet. So we're like at 10% of that, and we're not doing a lot of things that really aren't increasing our chances. So I don't know. Clock's ticking. We better get moving. Yeah. And then finally, after 8 or so billion years, again, remember, you wouldn't see this. This would be, the sun would be, again, red giant and obscuring your view. So maybe we say from some nice Earth-like planet elsewhere in the elsewhere in the Milky Way galaxy. Okay. So again, this thing, like this monster elliptical, it might have, I don't know, multiple supermassive black holes rattling around it. This is the veteran of many mergers. It's just vacuumed up stars and galaxies, everything in its path. Again, you can fit our Milky Way across the center. This is probably the veteran of a whole bunch of mergers. It wasn't born like this. It's been vacuuming up stars and material for billions of years. And if anything, again, the Hubble tuning fork is backwards, is you make things like this at the beginning of the galactic evolution, and then the more you perturb them, the less chance you have of making spiral arms and more chance you have of becoming an elliptical. Okay, any questions on that stuff? Yeah. If anything, yeah. So it's totally possible that right at the beginning of the galactic formation period, you could make any of these. But it's totally unlikely that if you just sat there watching an elliptical galaxy, in fact, it's impossible that if you just sat there watching an elliptical galaxy, it would like turn into a barred spiral or something like that. But if you sat there watching a barred spiral and something came along and bumped it, it could totally turn into an elliptical. So it would be so hard. So there are these some things about conservation of angular momentum, which would make it really difficult. So you have to start with a really high amount of angular momentum and kind of like feed matter onto them to make them. So to do it all at once, you just don't get the thing to, I don't know. So making one of these things is like taking a blob of pizza dough and very carefully throwing it up and spinning it out into a disk. You don't do it by putting it in a Christmas tree shaker or something. It's like too violent. You don't get it to work. So you have to be kind of gentle, I think, to make a spiral galaxy. Just like carefully feed matter onto a very rapidly spinning thing. But, yeah, okay, good. So we basically said it, but really quickly, Lookback Time and galactic evolution. So the second way of figuring out galactic evolution is literally to look back in time. And we can do that. So every image that you look at on Earth has closer and farther objects. So what's the farthest thing in the image? It's the mountain, and then closer is the airplane, and then closer is the people. And we're spoiled. And the reason that you're able to know that is because you know how big people actually are, airplanes actually are, and mountains actually are. But realize that they're all the same apparent size, basically, in this image. And we don't quite have that luxury with galaxies yet. For elliptical galaxies, we might not ever have that luxury because some are tiny, some are huge. But there's something else going on, is that in the imaging plane of this camera, when they took this picture, I think that it's not representing an image in time, in fact. It's kind of representing a continuum in time. Is that the people waving is the closest to the present, and then, a tenth of a billionth of a second later, further back in time is where I'm seeing the plane, and then I'm actually seeing the mountain farther back in time still, because it took light longer to get from the mountain and longer to get from the plane than it did to get from the people. You don't worry about this on a day-to-day basis, right? So because the mountain's farther, the light had to bounce off the mountain and travel all the way to the camera. The light from the person had to travel a shorter distance. In astronomical images, it's actually pretty important. And so you're actually seeing something, not like this image isn't amazing enough. You're actually seeing a lot more in it. So one thing is, it's kind of hard to tell who's close and who's far. And this almost looks like wallpaper, like a whole bunch of paint splatters, and they all seem to be the same apparent size. But just as the mountain, the plane, and the people might appear to be the same size, that's not really what's going on. And this is actually a huge cross-section in space. So it's this really long cone that goes far, far, far back into space. The second thing that's remarkable about it is when you're looking at this, you're actually looking at the entire history of the cosmos on kind of a cosmic scale. Is that this, just pretend that this is a close spiral galaxy. This is maybe 2 billion years ago. The light from this thing made it to the Hubble Space Telescope. And for these really far back ones, maybe that's about 8 or 9 billion years. So when you're looking at this, you're actually looking at, in addition to a whole bunch of galaxies, really cool, really tiny area of the sky, very cool. You're also actually looking at about 7 or 8 billion years of cosmic history, because it took that much time for the light from the really far things to get there. And we'll explain in a couple of minutes how this thing was actually created, but this is that's all we get. Somebody basically, not this one, but the Hubble Ultra Deep Field, they took it and they pulled apart all of the individual images of galaxies, all 10,000 of them, and using what we know about their distances, and we'll figure out how we know their distances, made a fly-through. This is really what you're seeing when you see the Hubble Ultra Deep Field, is it's a huge cross-section in space, but then also realize that you're going farther and farther back in time, because the light from this thing took, maybe 6 or 7 billion light years to get to you. I remember like 7 billion light years and probably 8 or so billion light years here. So this is really awesome. This is the equivalent of what rock layers are to geologists, where you go and you find, a side cut on a hill, and there are all the different layers, and you dig down, and you see woolly mammoths, and then after that you see dinosaur bones and stuff like that. This is the cosmic equivalent of that, is that if you look at something that's 6 billion light years away, how out of date is the light? 6 billion years. So how far back in time are you looking? 6 billion years. So you find something that's, 10 billion light years away, how far back in time are you looking? Yeah, and it's all in one image, so it's actually very nice. So this is almost like, again, like a side cut is to a geologist. You just go down through the layers and look back in time. So we'll use this for a lot more, but the first thing we'll use it for is getting a look at the evolution of galaxies. And the idea is basically you do something like that video did, and you cut it up into slices based on how far they are, and you sort them. So these are all the close spirals, SBAs, and these are all the medium far spirals, SBAs, and these are all the far spirals. And you make like kind of a flip book of their history. Just to make sure that we're doing okay on all of this stuff, because things get very weird very quickly in this class. So what is this? Yeah, it's got the refraction spikes, right? How far away is it? Guess, random order of magnitude guess is good. Yeah, it is within our galaxy, absolutely. So why don't we call it like 10,000 light years, 5,000 light years, something like that. Certainly less than 100,000 light years. Good. How far back in the past are we seeing it? Therefore, 10,000 years old, right? So what about this? So what type of galaxy is that? Yeah, spiral or barred spiral? Yeah, I believe you. It's hard, isn't it? Yeah, maybe that's a barred spiral and that's a spiral. Good, so spiral. How far away do you think it is? Just like total ballpark. If you get the number of zeros right, that's even very impressive. Billion light years away? Good. A couple billion light years away, 1 billion light years away? Perfect. So how far back in time are you looking when you see this? A couple billion light years away. Okay. So this one we have color only. So this thing, for the people in the back who can't quite see it, it's golden-ish. So what type of galaxy is this? It's an elliptical, because it's got no blue stars. Good. The ellipticals are reddish. And then how far away do you think it is? Tricky for ellipticals. Yeah, let's call it, more billion. 8 is good. Maybe that's on the high side, but yeah, good. And so how far back in time are you looking when you look at that? 8 billion years. And it's all in one image, which is really nice. Okay. So what you can do is you can take an image like that and you can make like a flip book of galactic lifetimes, where essentially what you're doing is you're saying that spirals all do the same thing. So you take close spirals and far spirals. The reason they look redder is because of two things. One is evil dust, and secondly, something called the cosmological redshift, which we'll get to by the end of the class, probably. And you can just make like a flip book. So these are the far away, therefore older, younger spiral galaxies, and these are the closer and therefore more contemporary spiral galaxies. And you can just kind of make like a flip book of the typical spiral's lifetime. And what you see is that there's kind of an age of galaxy formation. As new stars are formed all the time, but the age of galactic formation was the first like 2.5 billion years, maybe even a little bit less. And the second thing you see is these weird kind of dog-bony structures from really, really, really old galaxies. And he guesses about what these things are. So you don't even see the galaxy. They're so far away and they're so faint, but they all seem to have these things on them. It's the good four-letter word. So they don't necessarily have to be a merger, but they are pretty violent. They've got to be really bright if we can see them. And they seem to have this kind of axis to them. Jets. So they're the jets. So you see them in really, really, really young, just forming galaxies, which is why you don't see Andromeda doesn't have this. If Andromeda had a jet, it would be amazing. You would just see this streak covering the sky. So this would be upside and downside, and the galaxy itself would be in there. And remember, this is over 10 billion light years away. So this is, to see anything is amazing. So you're seeing like individual pixels and photons. Okay, but the short story is that galaxies seem to come from all the same time. Galaxies formed pretty early on in the universe. They're not constantly forming new galaxies now. Young galaxies tend to be more irregular in shape. So irregulars might be a preliminary stage of galactic formation. And young forming galaxies have jets. So here are nicer pictures of jets. And this is an active galactic nuclei, which means something happened to it, like a dwarf elliptical maybe just rolled right into its center or something. And this is a radio image. Okay, so this is 100,000 light years, like our whole Milky Way galaxy would fit in that, and I can put 3 or 4 of those along each branch of the jet. The visible galaxy itself is that big, so these things are monstrous. And it comes from the fact that there's a spinning supermassive black hole, really big magnetic fields, and it's just taking material and shooting it out along the magnetic field lines. Okay, so this solves an old problem. How many people have heard of the it's really quasi-stellar radio object? People have heard of quasars. It's just like random sci-fi jargon at some point in your life. Yeah. So in the late 1960s, people saw these sources first in radio and then followed up in observational light. And there's a galaxy, there's a galaxy, there's a galaxy, there's a galaxy. If I remove this label, what would you call this based on all of the images we've seen, in class? Look, it's got these spikes on it. So what does it really actually kind of look like? Yeah, it looks like a star. Because the refraction spikes come from the fact that it's basically a point source. It's almost like infinitesimally small. So the fact that this thing has refraction spikes, but it's equally bright as these things, and it's the same distance away, just really threw astronomers for like a loop. It was like the big thing in astronomy for a while. It's like, what are these bizarre things that are apparently the size of a star, but the brightness of an entire galaxy? Are there monster stars out in the past? And what this is the jet of an active galactic nucleus is pointing towards you. So something like basically the flashlight shining right in your eyes, and the core of the active galactic nucleus is so small that it basically takes on star-like characteristics. Basically acts like a point source. So those are quasars. And it's actually quasi-stellar radio objects, I think is the official acronym. People know what you mean. Okay. Questions about that stuff? So it's actually weird. the idea that light doesn't travel at instantaneously has been debated probably for longer than is recorded, but people were measuring it in like the 19th century to within like 1% of its known value. And then in 1865, Maxwell proved that it was wiggling electric and magnetic fields and said it must be equal to some value, and it was the theoretical value, and it's dead on accurate. So the fact that it goes at 3 times 10 to the 8th meters per second has been known for hundreds of years. And nobody really thought too seriously about the consequences of, because it took a long time to get parallax measurements, and even parallax measurements work out to like, 100 light years, so it's like 100 years out of date. So the fact that you can use it to probe cosmological distances is pretty new. But the fact that light travels at a finite speed has been, and that speed has kind of astronomical slowness, has been known for a long time. In fact, the orbits of Io around Jupiter, how you know the one of the first and best measurements of the speed of light. It's actually super clever, but it's kind of hard to describe nowish. But yeah, any other questions? Yeah. Yeah, all sorts of stuff happens. So you would absolutely get Doppler shifted, but there's also something called relativistic beaming that what's happening to you as a non-relativistic observer is that light is coming like kind of isotropically and hitting your eye. If you move close to the speed of light, these light rays actually all kind of, it's weird and it seems backwards. And it's one of those things that I would struggle to have like a clever analogy to explain, is that all of those light rays kind of bunch up. So you get this relativistic beaming effect where you can actually see behind you. Everything condenses to a dot in front of you, like the, when you near-death experience, tunnel of light, see grandma kind of thing. That's actually what, what special relativity predicts about traveling near the speed of light. And then everything gets very, very bright and the frequencies do change. But then there's also this weird kind of bunching effect too, which is actually why jets are jettier than it seems like they should be. So it's if you are moving at a relativistic speed, not only does the frequencies of light change, but then the way that they come and they hit you actually changes too. So objects would look deformed. If you were speeding relativistically past a star, and you actually could resolve the disk of the star, you would see light from this side and not from the other side, so it actually seemed like weird and warped. So I'll find some, especially if somebody reminds me, I can find some weird relativity videos. It's just everything looks really bizarro world. Because the light rays not only change in color, they also kind of change their distribution. It's very strange. Yeah. But yeah, it wouldn't look like things look